Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we'll discuss the dynamic braking and counter current braking of the separately excited or shunt DC motors. Last lecture, we stopped at the regenerative braking. For the previous classes, we described the speed control, starting, and regenerative braking of DC motors. And today, we will continue the remainder of the braking methods, which are dynamic and counter current braking. So the today objectives, inshallah, will be discussing the dynamic braking of DC motors, discussing counter current braking of DC motors, and finally we will discuss the course project, what is required when we will discuss the presentations and when you will submit the project, inshallah. Firstly, what is the counter current braking, or sometimes referred to as terminal voltage reversal, TVR. Counter current braking, simply, it means we need to stop the motor by reversing the current direction. What will happen if we reverse the current direction? Simply, if the current direction is reversed, the flux of the machine will be reversed, and the rotation of the machine in the positive direction will start to be resisted by the reversed flux. So the machine will stop. However, if we continue operating the machine with reverse supply, the machine will work as reverse motor. So in order to stop the machine, for braking, we need always to stop the machine. So in order to stop the machine, we have to add sensor to disconnect the machine supply at 0 speed. So this is the idea of counter current braking. We discussed it before for the three-phase induction motor, and today we will describe it in details for DC motor. So simply, as you can see here in the right-hand side, we have the circuit at motor operation in figure A, and when we need to make reverse current or counter current braking, we will oppose the DC supply in order to reflect or reverse the current direction. So simply on the motor characteristic, this is torque speed characteristic. For figure A, we can see this characteristic is for motor operation, and for characteristic B, which represents the reverse motor. But up till now, we speak about the forward motor and reverse motor. We didn't describe the braking, how we can stop this motor. We will describe it in the next slide. However, here we need to describe how we can reverse the current. Simply, we can reverse the current using the full bridge DC chopper, which is called class E DC chopper. For forward motor, simply we can operate Q1 with Q2, and we can discharge the signals using Q1 with D3. So this is the two modes for motor operation. And for reverse motor, we need to flow the current in that direction. So we need to operate switch Q3 with Q4 when we connect the supply, and when we need to disconnect the supply, we will turn on Q4 with D2. So this is the way of controlling the motor in forward and reverse motor. However, for braking, as we described, we need to stop the motor before reaching to reverse motor operation. So simply, this part represents the characteristic of the motor. So assume we have a certain active load torque. So this is our load torque, and 0.1 represents the motor operation. If we reverse the supply polarity, we will have the characteristic moving to reverse motor. However, we have to move at constant speed first. So we will move from 0.1 to the same characteristic but at 0.2, because no transition at variable speed. All of time the transitions will be at fixed speed. So at the same time, we are going to move the machine characteristic from point 1 to point 2. We described before this quadrant is called generator quadrant or regenerative braking quadrant. So even for counter current brake, we have to move from quadrant 1 to quadrant 2 at the regenerative braking, and at this instant the current is reversed. So this means the current is going to supply the source. However, here, here we still have source here. The source is reversed, and the current is going to supply the source itself. So at point 2, the machine is working at regenerative braking. Then the moving with the machine characteristic in order to reach to the load torque at point 4, in order to match the required load, we are going to move or cross at point 3. If you leave the motor with the load torque, it will move to point 4 and it will work in reverse motoring mode. However, for braking, we need to disconnect the motor at point 3 where the speed is 0. So the idea now, we need to make speed sensor, and based on this sensor, we are going to disconnect the motor at that point. So we can make very fast stopping using counter current braking in this way. A summary for our relations at point 1, point 2, 3, and 4. At point 1, this is the normal relations for motoring mode. We have V equal K multiplied by omega, which is EA or armature or back EMF, plus R multiplied by current, which is equal to torque load divided by K phi, and the current equation is the same, I1 equal to V terminal minus EA at point 1 divided by the armature resistance. For quadrant number 2, the current polarity is reversed, and the voltage also is reversed. So V2, which is equal to minus V1, equal to K phi multiplied by the speed, which is the same speed at point 1. So it's K phi multiplied by omega 1 plus R multiplied by current, which is torque divided by K phi. So this will be the equation of Kirchhoff voltage law of the DC machine, and the current value will be I2 equal to minus V1, because we have reversed the connection, minus EA1 divided by RA. Why still we use EA1? Because we're still working at the same speed. So these are the relations what we can use at point number 2. For point number 3, which represents 0 speed, so the EMF here will be 0. So at point 3, we can remove this part from the equation. So minus V1 equal to R multiplied by T3, which is the torque at that instant, divided by K phi. And the current can be calculated as minus V1 divided by RA. So these are the relations for point number 3. And point number 4 is the same relations of point number 1, but in reverse motoring. If we have a look to the currents at point number 3, as you can see, it's equal to minus V1 divided by RA. Assume we have a motor of 500 volts and the armature resistance is 0.1. So we expect here a current of 5,000 amperes. It's very huge current. Why we have very huge current here? Because the EMF is 0, which means the current will be very high at this portion. So what we can do, and the same also, by the way, the same also here for I2. The current at I2, because the polarity of V is reversed, you will find the numerator here is very high. So we will have very high currents at 0.2 and at 0.3 as well. So it's preferred, if you are going to make counter current break for DC motor, would prefer to add resistance in series with the supply. So if point A represents the motor at forward mode at quadrant number 1, when we need to make counter current break, we will reverse the supply polarity and also adding a braking resistor. This resistor needs to be calculated in order to limit the braking current. So simply at point number, instead of working at point number 2 now, we are going to work at point number 3, where we use here braking resistor. Our braking is greater than 0. So what will be the resistance used here in order to limit the current? Actually, it will be based on the value of current. So at point 3, we can substitute in the relations, but instead of RA, we have to add RA plus R brake. So the same relations as we described in the previous slides. However, we have RA plus RB. So from here, we can give the current, which is minus V minus E1 divided by RA plus RB. Finally, at point 4, which is the reverse motor operation, we can substitute with these relations. Minus V, because the supply voltage is reversed. K phi omega 4, because now the speed is changed to point number 4, plus RA multiplied by IA, which has a negative sign now, which is minus torque load divided by the machine constant K phi. So finally, I4 will equal to minus V1 minus E divided by RA. But here we still have braking resistor, so this relation is not correct. I will modify it in the slides and share it with you, and I will modify the slide and put it in the first slide of the video. Okay, Shabab? So at point 4, because at point 4 here, we still work with the same curve of adding resistance. Point 4, if we describe this point, not point 4, and if we assume this point, we call it as point 5 for instance. So we can say this point is a point number 5. So this relation can be applied for point number 5, not point number 4. So this is I5. However, I4, we have to add braking resistor. Okay, Shabab? So these are the relations that describe the reverse or counter current brake. So we can summarize the counter current brake or terminal voltage reversal in this table. So simply at point 1, which was operating in the motoring mode, we have the motor torque in positive sign, terminal voltage is still in positive, armature current in positive, speed in positive, field and EMF are in positive. At point 2, which represent the operation at quadrant number 2, where the torque is reversed and the current as well is reversed. So we have motor torque in negative, terminal volt. This is confusing a bit, but I don't like you to be confused. Take care here, we add this direction in negative because already we reversed the supply direction. However, there is no effect for the supply direction here now, because as you can see, The supply is reversed, however, the speed is still in the same direction because this point is just transient point. It will not stay long time. So, and we don't care about the terminal voltage at this instant because it's just transient. And you can find the armature current is already reversed because we work in the second quadrant. And also, we work at the same speed because this is just a transient transition between quadrant 2 and the quadrant 1. And the field is the same because we have no access to control the field here. This is separately excited one. And the EMF still in the same direction because the speed is still in positive sign. So this is considered as generating mode or regenerative mode. At point number 3, which means at the point that we have to disconnect the motor if we are going to break the motor. So the motor torque is in negative sign, the terminal voltage is negative sign, the armature current is negative sign, and the speed is 0. The field is the same direction, and the EMF will be 0 because we have 0 speed here. So this mode is called holding, or at the instant of disconnecting the machine. Finally, if we leave the motor to operate at point number 4, so we will have motor torque in negative sign, terminal voltage in negative, current in negative, speed in negative, and the field is the same, and EMF in negative. So it's still motor operation. If we compare between point number 4 and point number 1, you will find everything is reversed except the field because there is no access for the separately excited motor to control the field here. So you will find all of signs, torque, voltage, current, speed, and EMF, all of signs are reversed. So it's motor but in reverse direction. So this is simply the chart that summarizes the operation at counter current break. Here is an example. A DC motor has armature resistance of 1 ohm, constant, the machine constant K5 equal to 3 voltage second. When the motor terminal voltage is adjusted to 320 volt, the speed is 1000 RPM. So this is the terminal voltage and this is the operating speed. A TVR braking is applied. Calculate the braking resistor that would reduce the minimum braking current to twice of the rated value. So we are going to work in the characteristic where there is braking resistor. So we will work at characteristics at point 3 and 4. And if we are going to make braking, we will stop at that point. However, here it's just required to calculate the value of resistance that's going to make the characteristic moving in this drawing here at point 3 and 4. So we just need the value of resistance. How we can get the value of resistance? It's based on the current value. It's stated here, we need to limit the current to twice of the rated value. So firstly, we need to calculate the current at rated value. So from the motor operation at the first quadrant, we can calculate the rated current of the machine simply from the nameplate data. We have 320 volt and speed of 1000 RPM, and we know the value of K5. So simply I equal to V terminal or V line minus EA divided by RA. V is given 320. E we can calculate it by K5 multiplied by speed in rad per second. So RPM multiplied by divide 30. And divide by the value of the armature resistance, which is 1 ohm here. So we could calculate the current, which is 6 amps. So now the rated current of the machine is 6 amps. If we need to break the motor at twice of the rated value of rated current, so we need breaking current of 12 amps. So the breaking current will be 12 amps. This means the breaking current at point number 3 is 12 amps. So what will be the value of resistance here? So simply we can substitute the relations at point number 3. We have I braking now, which is 12 amps. So I brake equal to minus V, because the supply is reversed, minus E divided by RA plus RB. What will be the value of E? We're still working at the same speed. As you can see, this is the speed of our points. So speed at point number 3 is the same as speed at point number 1. So we will substitute with E as K phi multiplied by omega 1, which is given at 1000 RPM. So simply we can substitute in the relation, and you will have only one unknown, which is RB. So simply we can calculate the value of RB. As you can see, the value of RB here is very high. It's 51.8 ohms. It's very high compared to the armature resistance value. Armature resistance is 1 ohm only. So this is the value of braking resistance. But if you would like to calculate the current at point number 2 without any resistance, you will find the current is very high, which means here at that point, V minus E divided by RA. And if you calculate it, it will be this numerator divided by 1. So it's equal to that value. So it's a very high current. Okay, Shabab? Any question? Okay. Okay, this is the second type of the braking, which is counter current. So we described now regenerative braking, we described counter current braking, and the last type of braking, which is dynamic braking. Dynamic braking means we need to dissipate the stored energy, stored kinetic energy in the machine. We need to dissipate this energy into a resistive load, which means we need to disconnect the source of energy of the machine, which is a supply voltage, and just connect the resistance. And because there is stored energy in the machine inertia, this energy will be dissipated on the resistive loads. So simply the machine will stop, but after dissipating its energy on the resistance. So based on the value of the resistance, the stopping time will be. If we use very small value of resistance, this means we will have huge current and the stored energy will move in very fast way and the machine will stop very fast. However, this may be very dangerous to the machine because the current will be very high. For example, we can calculate the braking current based on disconnecting the machine supply. So we will have only the EMF connected in series with the armature resistance and braking resistance. So this is simply the circuit now. The circuit now is like that. This is the EMF of the motor. And this is the value of armature resistance. And now we have here the braking resistor. So this is our braking, and this is armature resistance, and this is E. So the current will be reversed in that direction and will dissipate the energy of the machine on the armature resistance and the braking resistance. Simply, if you didn't add braking resistance, a very huge current will move, which is equal to EA divided by RA. And simply in numbers, EA is very close to the terminal voltage. So if you assume for the last example, we have around 320 volts and the armature resistance of 1 ohm, so we'll have around 320 ampere. So we need to add braking resistor in order to reduce this current. So for this kind of braking, this is the value of current, or this is the relation of current. The total loss are mechanical, rotational loss, and copper loss. There is no any kind of losses either copper and rotational loss here now. So the copper loss will be very high because we will add resistance of breaking RB. So the machine dissipation of energy will just be dissipated in the braking resistor and the rotational losses itself. Rotational losses for any kind of machine are almost constant. So the stopping time will depend mainly on the copper loss, which is based here on the value of RB. Okay. So simply, this is the motor circuit. We will disconnect the supply of point A and add a braking resistor in the armature circuit. So based on the value of RB, the current will vary and the stopping time will vary. So for example, if we are working here in the characteristic at point A in the first quadrant, and we disconnected the supply and added a resistor, if RB is small like that, you will have high current. And this will stop the machine faster because the copper losses will be high, which means the energy consumption will be high and the stored energy will be dissipated faster. However, if you add small value of resistance, the current will be high value of resistance, the current will be small and the dissipation rate will be small and the stopping time will be high. So we can conclude that the higher the resistance value, the lower the braking current and the slower the machine shutdown. And oppositely, the smaller the braking resistance, the higher the braking current and the faster stopping. Right? Generally speaking, we can say very small resistance is very good now because it will fasten the machine stopping, will faster the machine stopping. However, we have limitation because of the value of current. All of time, we cannot increase the time over 2 or 3 times of the rated current. So we have to design our braking resistor carefully in order to avoid damaging the machine. Regarding the load types, we may have gravitational load type or other load type like compressors or fans or like that. For the previous characteristic here, this one for these two quadrants represents only loads like compressors, like fans. However, if we have gravitational loads, like for instance, the elevators or winches, if you left the machine at that point, what will happen? Simply the shaft of the machine is connected or coupled mechanically with the load, and the load will not stop. It can continue working in its direction and reverse the motor direction. So instead of moving the machine and stop it, it will reverse the speed of the machine, the direction of the machine, and start moving in that quadrant. So if we have gravitational load torque, like in elevators or like in winches, we can find that the operation can be extended to regenerative again, or generator, at the reverse mode. This is forward generator, and this is reverse generator. So we need to add something mechanically here to stop the motor in order to avoid moving with the load to the other side of generator. Otherwise, we are going to operate the machine again as generator because the load itself will be the supply, mechanical supply for the machine, which will work as generator. So this is simply gravitational characteristic torque speed for DC. Right. We can summarize the operation of dynamic braking in this graph, in this table. So at point number A, which represents the motor operation, we have positive torque, positive voltage, positive current, positive speed, field, and EMF. And here's the EMF in quadrant A, quadrant 1. EMF is lower than the terminal voltage. At quadrant number B, as you can see, torque is reversed because torque now in the negative side. At quadrant number 2, terminal voltage is 0 because we disconnected the supply voltage. We have no more supply voltage. Omega braking equal to omega A, and it's in the same direction. The field is the same because we are speaking about the separately excited, and the EMF here for point B will be the same for point A because we are working in the same speeds. In order to disconnect the motor at the origin points, at this case, we will have 0 torque and 0 current as well, 0 terminal voltage because there is no supply, 0 speed, and the field is not important now, and 0 EMF. And this represents no load case. However, we need to add mechanical latch in order to operate the motor at that point. Finally, at point C, if we left the motor to operate with the load, it will convert to generator mode, and at this instant, we'll find positive torque again. We'll have 0 terminal voltage. Armature current will be positive again, and the speed will be reversed. We don't care about field, and the EMF will be reversed as well. So this is a summary for the dynamic braking characteristics. Here is an example. The DC motor of previous example is loaded by gravitational load. The motor current is 40 amps at steady state condition. So at steady state, the current is 40 amps, and gravitational load, which means if there is no mechanical latch for the machine will work at point number C, which represents the generator mode. If the DC source is replaced by braking resistor of 2 ohms, so this is a value of RB. Calculate the motor speed at new steady state operating point. So simply, the new operating point will be point number C. Why we select point number C, not point number B, Shabab? This is a question for you. Why here we will solve at point number C, and you can return back again to the characteristic. Why you are not going to work at point number B here in this example?
Because the motor will try to reach the torque applied by the load.
Okay, it's right, but what is said here in the problem to say that? As you can see.
Steady state.
Huh?
Steady state.
Yes, the word steady state. This is the word now. Because point B is transient point. Is it right? Point B is transient, and point C will be the steady state point of the machine. And there is no nothing mentioned regarding mechanical latch that is going to stop the machine at the origin. So we will calculate our requirements based on the steady state operation at point number C. So simply, at point number C, the steady state current will equal to EMF divided by RA plus RB, but in minus sign. So EMF will, the current is 40 amps, EMF equal to K phi multiplied by the speed, which is required here, divided by the armature resistance plus the value of braking resistance. Finally, we can get the RPM of the machine. Okay. Another example here, a DC motor has the following data: 81.5 ampere, 15 kilowatt, 220 volt, 1600 RPM, and armature resistance of 0.167 ohm. Calculate the braking resistor required to stop the motor if the motor was working at 1630 RPM, given that the motor current has to not exceed the current where the load torque is 180 Newton meters. So now we need to calculate the value of braking resistor based on a set value for current. And here the current is given by means of the electrical torque or load torque. So simply, we need to apply Kirchhoff voltage law and calculate the value of resistance based on the current value. Here we don't have any supply voltage, so we can redraw our circuit here. So we have we have the EMF of the machine. This is EA, and we have braking resistor and armature resistor. So this is RA, this is R braking, and we have current I braking. So simply, we can first calculate the machine no load speed. So simply speed equal to 2 pi multiplied by 1600 divided by 60. So this is the value of omega naught, and Tn, the rated torque, equal to the power divided by that speed, which is 15,000 kilowatts, divided by the omega, which is 89 Newton meter. So rated torque is 89 Newton meter. And can you see here, it's required to stop the machine at 180 Newton meter. So it's around 2 times, is it right? 2 times of the rated torque, which means also 2 times of the rated current. So simply from here, we can calculate K phi. So K phi equal to E divided by omega. And we have the value of V and the current at full load. And simply we can calculate K phi and use the braking speed, which is 1630. Braking speed equal to IAR total divided by K phi, which is EF I multiplied by R total from the circuit here, which is EF or EA of the machine, the back EMF. So simply we can substitute instead of I, we can substitute by torque divided by K phi. So torque multiplied by R total divided by K phi squared will equal to the machine speed. So simply we can substitute in this relation and we can find the only unknown here, which is R total. And we have the value of armature resistance, which is 0.167, and we can finally calculate the braking resistor. So the braking resistor is 1.23 ohms, which is required to limit the current to approximately twice of the rated current. Any question here, Shabab? Everything is clear?
Yes.
Okay. How we can control the value of braking resistor? I mean, if you go to the market and said to developers, I need resistor, for example, with this value, 1.33, 1.233. Is it easy to find that resistance? It's not easy. So we need something to make accurate resistance. I mean, in industrial شباب, if you can find resistor of 1 ohm, it will be stated the accuracy, it's plus, for instance, 10%, 5%, like that. However, if you can find resistance with tolerance of 1%, it will be very, very expensive. So it's not easy to obtain a resistance with very small values or very accurate values like we need in these operations. So we need to make a technique that can control the value of resistance. Simply, if we have our motor like that, and we added switch in parallel with the resistance, we can simply control the value of this resistance by controlling the switch. So for instance, the current which is going to move here, IA will be divided to IC and IB. IB, which is the braking resistor current, and IC, which is moving in this switch. So we can say IB equal to IA multiplied by 1 minus K, where K is the duty cycle, which means if this is IA, armature current, and we turned the switch for that portion, so during this switch on, the current is going to move here, not in the resistance, because this switch will act like short circuit on the resistance. So when the switch is on, all of current or armature current will move in the switch. And if the switch is off, the armature current will move here in the braking resistor. So the braking current will be at that part and will equal to the armature current. So simply, we can say the braking current equal to 1 minus K as average value, 1 minus K multiplied by the value of armature current. So by controlling K now, we can control the value of braking current. So simply, you can bring the resistance, and by controlling the duty cycle of this DC chopper, we can control the value of the braking resistance. So if we need, for example, VB equal to IARB, so the braking voltage here equal to IA multiplied by RB multiplied by 1 minus K. We just substituted VB equal to IBRB, so IB equal IA multiplied by 1 minus K. So IARB multiplied by 1 minus K, which is EA minus IARA. V equal to EA multiplied minus IARA. So from here we can get the R equivalent, which is equal to VB divided by IA. So this is the braking voltage, VB, between these two terminals. And simply we need to calculate the resistance of that part. So assume we have like 2-port network here, and we need to calculate the resistance between these points. So from here at that side, we need to calculate the resistance seen by the supply. So we can simply divide VB by the armature current. So VB divided by the armature current will give you the value of R equivalent seen by the motor, which is equal to V braking like that divided by IA. So it will be RB multiplied by 1 minus K. So this value will represent the equivalent resistance seen by the motor. And simply the power consumed in the braking resistor will equal to IA squared multiplied by the equivalent resistance. So this is the way to control the value of resistance of the braking.
So,
So
can you repeat that again? Repeat the last point again, please.
last point. Okay. As you can see here, we need to find the value of R equivalent here. Why? R equivalent represents the breaking resistor value that we need to control in order to avoid high current and also in order to stop the machine very fast. So simply, how we can control R equivalent? R equivalent, you know Thevenin equivalent circuit. In order to get R Thevenin, we just divide V Thevenin divide I Thevenin, or V open circuit divided by I short circuit. This is the way to get the R equivalent between 2 points. So simply, we calculated that we have breaking voltage here. This is plus and this is minus, and this is VB. So VB equal to R equivalent multiplied by IA. So we can say R equivalent equal to VB divided by IA. And simply we calculated VB here, which is equal to IARB multiplied by 1 minus K. So substitute here VB divided IA, you will find the R equivalent equal to RB multiplied by 1 minus K. So by controlling the K, you can control the value of R equivalent. So we can bring a high value of resistance. For example, for the last problem, we need 1.23 something. Simply, you can bring a resistor of 2-3 ohms. And by controlling the value of K, you can control the R equivalent. So because you cannot find very accurate resistance in the market. So bring in a resistor and use this chopper in order to get very accurate resistance value. تفضل. تفضل زياد.
دكتور، طيب بالنسبة للباور حق الريزستور، صعب اننا نحصل هاي باور ريزستور.
For the resistor power, for that we need to calculate the resistor power. The question again, how much power we need in order to buy resistance. For that we need to calculate the power dissipated on the resistance. So we calculated here power breaking equal to IA square multiplied by RB multiplied by minus K. So based on this value, you need to specify your resistance. And if we apply that to the previous example, we have here I breaking, which was equal to twice of the rated current approximately. Rated current was 81. So multiply this value by 2. So it's 163 ampere. Okay. And calculate the power of the breaking resistor. So I square multiplied by R required here, which is 1.233. So simply we can say here power break equal to I break square R break, which is equal to 2 multiplied by 81.5 square multiplied by 1.233. Okay, so this will give you the value of the power in watts. Okay, شباب, based on this value, we have to specify our resistance. In order to buy any resistance, you need to specify the power value and the resistance value. So simply, this is the way to calculate the breaking resistor. Any question?
دكتور.
Yes, fine.
بالنسبة للريزستور، هل حصل أنا حسبتها طلع 32 كيلو واط، هل راح أحصل زي كذا في السوق؟
طبعا for this kind of machine, let's return back to the example again. This machine is 15 kilowatts. Okay, it's not that huge. However, the power needed here, when we calculate it, it's around what? 30 kilowatts.
32 كيلو وات.
يعني this amount is very high now, and it's not easy to find in industry. However, يعني it's not possible. You can find, but it's not easy to find. Okay. طبعا we have many methods for breaking يا شباب. if we have a problem with the resistance value, we can use any other technique. If we cannot find suitable resistance, we can find any other technique. Right. Take care also here, the duty cycle is a factor affecting the power breaking. And you can reduce the power a bit by controlling also the value of K. However, you have to compromise between R equivalent and power in order to stop the machine at any suitable time. Right. Any questions, Shabab? Okay. Regarding the projects, we will just review the 4-quadrant operation quickly. We described last class, we can make the control of the machine in the 4 quadrants using this circuit, which is called Class E DC chopper. And this is these are the different modes of operation for the 4 quadrants. So simply by following this sequence of pulses, S1 and S4 on, you can find S1 and S4 operating the machine in forward mode. And if S4 and D2 are on or conducting, S4 and D2 conducting, you will make short circuit on the machine, which means you can control the value of armature voltage. Again, this part, by controlling S1 in that way, as you can see, the 2 modes here, S4 is open, is on for both of cases. So this is S1 and S4 will be open all of time for motoring operation. So this is on time. Let's say this is T1 and this is T. And the diode will conduct only during that part. So if this is S1, what will be the output voltage on the motor, which is VA? If we assume we have supply V, and this is the value of V, what will be the value of VA? Shabab, it's a question for you. Any answer?
I think it will be the on time over the total time times the VA.
on the shape for the figure. In this figure, at the instant of S1 and S4 on, the V voltage on the machine will be the same value of V, like that. صح يا شباب؟ So this is the value of V now, okay? And it will be repeated again here. So based on that, if T1 divide T equal K, so we expect VA equal to K multiplied by V. Is it right?
Yes.
As average value type. So we can control the machine speed in the first quadrant here by controlling the value of K. So in this phase or this mode, we can control the machine speed by voltage control. How? Just by controlling K, which means controlling the value of T by using pulse width modulation, or we call it here as duty cycle control. Yeah, شباب, we stated before, we can control T1, and this is called pulse width modulation, and we can control T, and this is called frequency modulation. So, and we prefer fixing T with certain switching frequency, for instance, 5 kilohertz, 10 kilohertz, like that, and control the value of T1 based on the T in order to have K, duty ratio, from 0 to unity. So this is a way to control the DC chopper as the motoring mode. Right. For the other modes, we have to do the same functions by controlling also switches and diode in that way. So controlling switches, and with the help of diode conducting, we can control the machine. Right. Now, in order to control the motor in forward mode and reverse mode, we need to apply some pulses to this circuit. First, we will apply to S1 with S4, and based on the value of duty cycle here, we can obtain certain voltage to get certain speed. So we can make closed loop control for the speed, and the action of the PI controller will be translated to the value of K, which will control the machine speed. Okay, شباب, is it clear? Simply, we can do the same in reverse mode. In reverse mode, we need to apply switching pulses for S2 and S3. And as you can see here, S2 was diode D4. So this means S2 in this mode will be on all of time, and S3 will be controlled on and off in order to control the machine speed. The same is also can be done for generator or reverse generator. Okay, شباب? Right. So simply, what is required from you in the project? The project said here, design a complete drive system for the DC motor used in EE462 laboratory. We have already calculated the machine parameters last experiment. So based on these machine parameters and your nameplate data, make a mathematical model for the machine and control this machine using 4-quadrant DC chopper. It's required to control the machine or to operate the machine in the 4-quadrant modes. What is the expected project outcomes? We need simulation model using MATLAB Simulink. You have to operate the motor or the machine at the 4 quadrants. After designing your simulation model, you need to make a report. In the report, you need to discuss the operation of the 4 quadrants of the drive system and summarize or add the results of the MATLAB simulation for the 4-quadrant operation. So expect to have, for instance, the machine speed, the torque, machine torque and speed and voltage, okay? The machine current. So for now, current, volt, torque, and speed. We need to see all of these curves with time. And also, a calculation sheet for the drive system component sizing and selection. Selection for suitable for the full load condition. So you need to calculate the elements required for this drive system. For instance, we need to make speed control. So what is the rated voltage of the machine? Say, for example, 250 volt. So what will be the supply voltage of the DC chopper? Is it going to be also 250 or higher? And we can control the voltage using DC chopper. What is the machine, what is the supply currents? So it's based on the machine current, okay, and your calculations. Based on what? Based on the full load condition of the machine. So this is called the calculation sheets for the operation of the machine. And for the sizing, I mean, sizing means in order to buy these values from industry, what will be the values? For instance, I'm going to buy a source, so I have to specify the voltage